Hello everyone, it's me, Mr. Younger. It's July 9th, Thursday morning, about 8 a.m. We are meeting to discuss our second lab for this week, and this week's second lab is a little bit off the beaten path. I didn't plot this as our typical lab that we're going to do this part in the semester, but I decided to at the last minute. So this lab is actually called the ballistic pendulum. We actually just solved a problem like this in our lectures on ballistic pendulums, so you have some sense of knowing what's going on. But basically, you fire a projectile into a pendulum, uh, and conservation of momentum for that initial collision allows us to determine what the speed of that pendulum is the instant after the projectile embeds inside of that pendulum. And then from that point on, you can use conservation of energy to take and turn the kinetic energy of that particular pendulum with the embedded projectile in it. You can use that kinetic energy equal to the final potential energy to figure out what the initial velocity of the projectile was. So that's what the ballistic pendulum is about. And it's, like I said, a real life application we use, for instance, determining the muzzle velocities of guns and things of that sort. So let me go ahead and share my screen with you so you'll we can discuss what's going on. This is the module in which your lab is this week. We already did the physical pendulum. Now we're doing the ballistic pendulum. This is the lab write up for the ballistic pendulum, and then this is the addendum that allows us to get it done from home. And this is where you're going to turn it in. And I haven't set the due date on that yet, and I didn't put all the details. But like I said, you can always go back to like week lab 7 or lab 8 or something like that to see the instructions, because it's literally the same instructions every time. So I'm not too worried about not necessarily putting them in there every time. I try to, and just right now it's not a big deal. So, anyways, this assignment group is, oh yeah, that's right. I already fixed that. The submission is online, and it has to be a file upload, but it can only be a PDF file. And it will be due a week from today, which is the 16th, and we make that at 11:59 p.m. And that's it. We now have this assignment set up appropriately so that we can see uh, what's going on. But that's where you actually would turn it in. I'm going to go back to the modules now that you've seen the whole module for this week, showing Tuesday's labs as well as this lab. I'm going to go ahead and show you what's in the document that we call Ballistic Pendulum Lab. So just referring to this again. Oops, went too far. Here I am. So I'm going to open this document next, and I've already got it open technically. And here it says Lab 11. It's actually, the file is called like Sequence 1 Lab 13 or something. So that's why you'll see a different, yeah, that's what it is. That's why you'll see a different title pop up. So this is the projectile launcher that we have in our lab, and this is the actual pendulum we have. It's a particularly well-designed device that has a very specific weight, a very specific center of gravity, a nearly frictionless joint, or I should say hinge, that allows it to swing out. It's got a little marker here that you can pull all the way down to zero or close to zero, but really they just recommend you set it to an angle lower than you're pretty confident this is going to go, and then you fire the projectile that swings up, and whatever the max height it reaches, this little thing will dial up and tell you what that angle was, and we can use that angle to figure out, of course, the initial velocity, which is the whole point. Now, they've worked this out here in terms of kinematic equations. For instance, delta y equals 1/2 gt squared, and implies that the time required is the square root of 2 delta y over g. And that's actually so you can first determine the velocity of the projectile. So what you're going to do is you can take this pendulum and hang it up out of the way, and then you can fire the projectile, and it'll be fired off a horizontal surface, or excuse me, fired horizontally off of a surface of height delta y. And from that, you can determine basically how long it's going to be in the air, because that's how long it'll be able to move horizontally. So the amount of time it spends in the air is t equals the square root of 2 times delta y, and delta y should be the height from the bottom of the ball to the ground, or to the floor where it's going to hit. And we assume the floor is all level. It might not be that level, but still we assume it's level. And then you measure the height from the floor adjacent to the launcher up to ideally the bottom part of this ball, and measure piecing that measurement together, that gives us the height delta y. And this equation, once we solve it for t, is this form. So you take the square root of 2 times delta y over g, and that gives you the time in the air. And then you measure the delta x, which is basically how far it launches horizontally before it hits the ground. So that horizontal distance delta x is another measurement we'll make, and from that we can take and realize that the horizontal velocity is going to be a constant. So you can assume the average velocity is the velocity, and velocity is distance divided by time. So the muzzle velocity by this method should be equal to delta x divided by the time, and of course the time was 2 delta y over g. So this is one way of determining the initial speed of the projectile. Another way, of course, is using the ballistic pendulum, and that's where they go here. Here's the kinetic energy, or excuse me, here's the momentum of the small ball, the projectile. When it's initially fired, we assume it has the same velocity v0 that we learned before, and then immediately after the collision, the new momentum is big M times little v, where big M is actually going to be the mass of the ball plus the pendulum. And with that in mind, you could solve, for instance, for the new v, and that new v, of course, would be given by little m over big M times the original v, and now we have that velocity. Now we can use conservation of energy for the part where it's now left the collision, but it's in the process of swinging up. We can use conservation of energy for that. As I said, all the terms drop out except for the initial kinetic energy, 1/2 big mv squared, and the initial, or in the final potential energy, which is big mgh. So if you plug in the v that we just found here, into here and square it, you'll get an expression for the initial velocity, and that expression is this. And I did all this derivation in a lecture on chapter 9. I think it was one of the last, or probably second or third from last problems I did in the chapter 9 conservation of momentum chapter. So that's the actual result. That's what you're testing. In this case, we have to convert the h, or we have to get the h in terms of the angle theta, and that's all you have to do. Once you know the radius of the center of mass of the actual ballistic pendulum, then you can just multiply that by 1 minus cosine of the angle theta, where theta is the angle that the launcher reads at its highest point. You know, you obviously do multiple trials or whatever. The main thing is you get a estimate of what the angle is on average for several trials, and then you plug all this in, and that should give you the initial velocity. And that initial velocity can, of course, be compared to the initial velocity that we got this way as well. So, anyways, what we normally do in this scenario is you fire the projectile from the projectile launcher, and it would land on a piece of carbon paper, and we could measure the center of, basically the center of the bottom of the ball. We can measure that horizontally from here to here, and that'll give us delta x. But we can measure from the bottom of the ball to the top of the floor right here, which should be the same height as this part, and that'll give us the delta y that we needed. And we have, of course, a pizza box back here, so the projectile, once it bounces off the carbon papers and then lands, hits the back of the box, it won't roll all over the place. That's the main purpose for that. Now, what we were supposed to do in the original document is you determine delta x for 5 different trials with the same setting on the projectile launcher each time. From that, you get a delta x average in meters, and you measure delta y. That's a figure that you just put in, so delta y in meters, and then you calculate what the initial velocity is. We're using the formula square root of 2 delta y over g, if I remember correctly, whatever the formula is right here. 2 delta y over g is the time, right? So you use that, and then you take the velocity, the delta x, and divide it by that time. So delta x over the square root of 2 delta y over g gives you the velocity v0. So that's what goes there. And then you're going to do the angular displacement of the pendulum arm. In that case, you're going to do 5 trials of the angles, and you're going to get the 5 angles, take the average, and then you can use m and m plus big M, which is what big M is actually the mass of the little m uh, plus the weight of the ballistic pendulum. So that's what goes in here. And the R center of mass, we can just measure down to where it marks on the center of mass. The muzzle speed from part A, the muzzle speed from part B, percent difference, and then the best estimate for V0 would obviously be probably the average of the two. So if you just take the average of the two different ways, that's probably the best estimate of what the initial V0 is. Then you have some questions to answer and calculations to do. These are not sample calcs. These are actual calculations to make sure you understand the theory behind the lab and stuff like that. So that must be done. And you guys are 241 students, so this is another thing that you can do. The 201 students wouldn't necessarily do that because they're algebra based, but these students are calculus based. So anyway, so that's the ballistic pendulum document. Now I want to show you the ballistic pendulum addendum. That was the next thing. If you look right here, you'll see we just finished looking at that. Now we're looking at this addendum. The addendum is right here. And you can see what it says is data page 3. Here's your 5 trials of delta x. Here's your delta y. Here's your 5 trials of the angle. Here's your lowercase m. Here's your uppercase M. And here's the R for the center of mass. With this data, the muzzle velocity from the firing of the tables was 4.88, and the muzzle velocity using conservation of momentum turned out to be 4.94. That's what I got when I did this, so that should be comparable to yours. If you get something different than that, then there's a good chance you made some kind of calculational error. And it's okay. I don't mind you having it up front. You know, that's one of the things we check, is sometimes we'll have cheater things just to compare, and sometimes we give them to you up front, and sometimes we don't. In this case, I chose to just go ahead and give it to you so you know what you're working for, because this is part of the semester where we're still trying to make sure you guys know how to apply conservation of momentum, conservation of energy, and that sort of thing. So anyways, that's the lab in its entirety. This gives you all the information you need. I don't think I have any videos on the procedure, but if I do, I'll try to put it just ahead of this in the same module, but just ahead of the document that says ballistic pendulum lab. So anyways, that's about it. I'm going to go ahead and stop sharing the screen. As always, I try to have this 8 a.m. class on Tuesdays and Thursdays that is not only an intro to lab for that Tuesday or that Thursday, but it's also a potential office hour for anybody that might have questions. And of course, I ended up having to miss last night because the storms knocked out my Wi-Fi. So I wanted to make sure I got here in time in case anybody had any questions. But there's nobody here this time, so I guess I'll just call it a day. Feel free to preferably text me, but you can also email me if you need to set up a time. I can set up a Zoom meeting. You can, if you wait till Monday, I could actually come in and meet you somewhere sometime. Of course, I have office hours at class or at school that day. I have office hours at school on Wednesdays as well, but I can also make office hours at other times, either by Zoom or by going to a location. So just let me know. I'm here to help you. I want you guys to succeed. So let's do as good as you can. Have a good day, and thanks for coming. Bye bye.